Antiparticles, 1930 to 1956. Non-relativistic quantum mechanics was completed in the astonishingly brief period 1923 to 1926, but the relativistic version proved to be a much thornier problem. The first major achievement was Dirac's discovery in 1927 of the equation that bears his name. The Dirac equation was supposed to describe free electrons with energy given by the relativistic formula E square minus P square C square equal m square C to the power 4. But it had a very troubling feature. For every positive energy solution, E equal plus root over P square C square plus m square C to the power 4, it admitted a corresponding solution with negative energy E equal minus root over P square C square plus m square C to the power 4. This meant, given the natural tendency of every system to evolve in the direction of lower energy, that the electron should run away to increasingly negative states, radiating off an infinite amount of energy in the process. To rescue his equation, Dirac proposed a resolution that made up in brilliance for what it lacked in plausibility. He postulated that the negative energy states are all filled by an infinite sea of electrons. Because this sea is always there and perfectly uniform, it exerts no net force on anything, and we are not normally aware of it. Dirac then invoked the Pauli exclusion principle, which says that no two electrons can occupy the same state, to explain why the electrons we do observe are confined to the positive energy states. But if this is true, then what happens when we impart to one of the electrons in the sea an energy sufficient to knock it into a positive energy state? The absence of the expected electron in the sea would be interpreted as a net positive charge in that location, and the absence of its expected negative energy would be seen as a net positive energy. Thus, a hole in the sea would function as an ordinary particle with positive energy and positive charge. Dirac at first hoped that these holes might be protons, but it was soon apparent that they had to carry the same mass as the electron itself, 2000 times too light to be a proton. No such particle was known at the time, and Dirac's theory appeared to be in trouble. What may have seemed a fatal defect in 1930, however, turned into a spectacular triumph in late 1931 with Anderson's discovery of the positron, figure 1.5, a positively charged twin for the electron with precisely the attributes Dirac required. Figure 1.5, the positron. In 1932, Anderson took this photograph of the track left in a cloud chamber by a cosmic ray particle. The chamber was placed in a magnetic field pointing into the page, which caused the particle to travel in a curve. But was it a negative charge traveling downward or a positive charge traveling upward? In order to tell, Anderson had placed a lead plate across the center of the chamber, the thick horizontal line in the photograph. A particle passing through the plate slows down and subsequently moves in a tighter circle. By inspection of the curves, it is clear that this particle travelled upward and hence must have been positively charged. From the curvature of the track and from its texture, Anderson was able to show that the mass of the particle was close to that of the electron. Photo courtesy, California Institute of Technology. Still, many physicists were uncomfortable with the notion that we are awash in an infinite sea of invisible electrons, and in the 40s, Stuckelberg and Feynman provided a much simpler and more compelling interpretation of the negative energy states. In the Feynman-Stuckelberg formulation, the negative energy solutions are re-expressed as positive energy states of a different particle, the positron. The electron and positron appear on an equal footing and there is no need for Dirac's electron sea or for its mysterious holes. We will see in chapter 7 how the modern interpretation works. Meantime, it turned out that the dualism in Dirac's equation is a profound and universal feature of quantum field theory. For every kind of particle, there must exist a corresponding antiparticle with the same mass but opposite electric charge. The positron then is the anti-electron. Actually, it is in principle completely arbitrary which one you call the particle and which the antiparticle. I could just as well have said that the electron is the antipositron. But since there are a lot of electrons around and not so many positrons, we tend to think of electrons as matter and positrons as antimatter. The negatively charged antiproton was first observed experimentally at the Berkeley Beaverton in 1955 and the neutral antineutron was discovered at the same facility the following year. The standard notation for antiparticles is an overbar. For example, P denotes the proton and P bar the antiproton, N the neutron and N bar the antineutron. However, in some cases it is more customary simply to specify the charge. Thus, most people write E plus for the positron, not E bar, and mu plus for the anti-muon, not mu bar. But you must not mix conventions. E bar positive is ambiguous like a double negative. The reader doesn't know if you mean the positron or the antipositron, which is to say the electron. Some neutral particles are their own antiparticles. For example, the photon, gamma bar equal gamma. In fact, you may have been wondering how the antineutron differs physically from the neutron, since both are uncharged. The answer is that neutrons carry other quantum numbers besides charge, in particular baryon number, which change sign for the antiparticle. Moreover, although its net charge is 0, the neutron does have a charge structure, positive at the center and at the edges, negative in between, and a magnetic dipole moment. These two have the opposite sign for N bar. There is a general principle in particle physics that goes under the name of crossing symmetry. Suppose that a reaction of the form A plus B to C plus D is known to occur. Any of these particles can be crossed over to the other side of the equation provided it is turned into its antiparticle, and the resulting interaction will also be allowed. For example, A to B bar plus C plus D, A plus C bar to B bar plus D, C bar plus D bar to A bar plus B bar. In addition, the reverse reaction occurs, C plus D to A plus B, but technically this derives from the principle of detailed balance rather than from crossing symmetry. Indeed, as we shall see, the calculations involved in these various reactions are practically identical. We might also regard them as different manifestations of the same fundamental process. Now, there is one important caveat in this. Conservation of energy may veto a reaction that is otherwise permissible. For example, if A weighs less than the sum of B, C and D, then the decay A to B bar plus C plus D cannot occur. Similarly, if A and C are light, whereas B and D are heavy, then the reaction A plus C bar to B bar plus D will not take place unless the initial kinetic energy exceeds a certain threshold value. So perhaps I should say that the crossed or reversed reaction is dynamically permissible, but it may or may not be kinematically allowed. The power and beauty of crossing symmetry can scarcely be exaggerated. It tells us, for instance, that Compton scattering photon plus electron to photon plus electron is really the same process as pair annihilation, electron plus positron to photon plus photon, although in the laboratory they are completely different phenomena. The union of special relativity and quantum mechanics then leads to a pleasing matter or antimatter symmetry. But this raises a disturbing question. How come our world is populated with protons, neutrons and electrons instead of antiprotons, antineutrons and positrons? Matter and antimatter cannot coexist for long. If a particle meets its antiparticle, they annihilate. So maybe it's just a historical accident that in our corner of the universe there happened to be more matter than antimatter, and pair annihilation has eliminated all but a leftover residue of matter. If this is so, then presumably there are other regions of space in which antimatter predominates. Unfortunately, the astronomical evidence is pretty compelling that all of the observable universe is made of ordinary matter. Recently, Wilczek and others have put forward a possible explanation for this cosmic asymmetry. I shall not go into it here, but if you are interested, I recommend Wilczek's article in Scientific American, December 1980.